So this is exercise 10F, question 5. As a box P of mass 2.5 kilograms rests on a rough horizontal table and is attached to one end of a light inextensible string. The string passes over a smooth fit pulley fixed at the edge of a table. The other end of the string is attached to a sphere Q with mass 1.5 kilograms and hangs freely below the pulley. The magnitude of the frictional force between P and the table is K newtons. The system is released from rest with the string taut. After release, Q descends 0.8 meters in 0.75 seconds. Modeling P and Q as particles, calculate the acceleration of Q. So what we're going to need to do, I think I'll just do my force diagram quickly first. I'm just going to do it on top of here. So what forces are acting? Well, there's going to be a weight component for both particles. Because P is on a surface, there's also going to be a reaction over here. It's on a rough surface, and so there's going to be K, which was the frictional force, and there's a piece of string, so there's going to be tension. And we're told that Q descends, so it's going to go this way, and P is going to end up going like that. So that's our force diagram. Just quickly done that. And then it tells us to calculate the acceleration for Q. But they gave us, they told us it starts from rest, they told us the displacement or the distance, and they told us the time. So this is going to be a SUVAC question. So S was 0.8, U was 0, V we don't know, A is what we're trying to work out, and T equals 0.75. And guess what? We're going to have to use S equals UT plus half AT squared. Every time we don't have V, no information about V, we're going to have to use that equation, and that happens a lot. So let's just go with S equals UT plus a half AT squared, and 0.8 is equal to 0 times 0.75 plus a half a t squared. So it's going to be 0.8, this term becomes 0, and 0.75 squared is, well, that's 3/4, and 3/4 squared is 9/16. So this is going to be half times 9/16 times A. And if you rearrange that to work out A, you get A as 128/45. In decimals, that comes out as 2.8 meters per second squared. I'm going to leave it and I'm going to use the fractional version because I've done a bit of rounding here. It comes out as 2.84, etc. But so because I've rounded and to give me 2.8, here, actually just thinking, we did not use G. We didn't use any G within this whole calculation. So if you're going to give your answer in decimals, you should give it as 3 sig fig. Right? The only time we give our answer to 2 sig fig is when we use G. And we did do that in this code. So if you give it as fractions, 2.84. Next bit says, show that the tension in the string is 10.4. So to find the tension, I'm going to look at particle Q. So I'm going to look at this section of information there. So I'll just redraw it quickly. Particle Q had a weight of 1.5 g, had a tension going up, and it had an acceleration downwards of, and as I said, I'm going to use the fraction answer so I don't lose any accuracy in my answer. Right. So if we if we find our resultant going downwards, then we've got 1.5 g, that's the force acting downwards. The force acting upwards is tension, so we subtract them to get our net force. and the net force is equal to mass times acceleration. And if we rearrange, G is 9.8, remember. Oops, I want to do a minus there. 1.5 times 128 over 45, and that will give us our tension. And we've been asked to give it, so I calculated it and give it 313 over 30 as a decimal, but we've been asked, sorry, as a fraction, but we've been asked for it as 3 sig fig, so it's going to be 10.4 newtons. And so this wasn't part B, this was part II. And then we're asked for III. We're asked to work out K. So K is the frictional force that's acting on P, so we're probably going to have to use particle P. Okay, good. And then the acceleration, let's put that in, was 128 over 45. So if we calculate our resultant going to the right this time, because acceleration is to the right, then you've got tension pulling it forwards, and you've got K pulling it backwards, and that's equal to mass times acceleration. We already knew our tension, and you've drawn the arrow from 10.4. Actually, I'm going to rub that out. I'm going to use the fractions, and as much as you can use fractions, that's going to be better. It's going to give you the most accurate possible answer. So it's going to be 313 over 30, take away 2.5 times by 128 over 45, and that's going to give us K. And so K in fractional form comes out as 299 over 90, and in decimals it's 3.3 newtons. This time we did use G. We have used G to calculate this, and so we're going to need to give our answer to 2 sig fig. And finally, in part B, it says state how in your calculations you have used the information that the string is inextensible, and because the string can't be expanded or contracted, it means that the tension is going to be the same on either side of the pulley. So the tension acting on both the particles is going to be the same, the two tensions there. Okay, thanks for listening. That's the end of this one.